I think we can start. Okay. Good afternoon, everyone, and welcome to the quantity engineering control seminar. It's my honor to host Professor John Ringwood visit to UM to talk about a very special control program, ocean wave energy control. In 2017, when I attended the European Wave Energy Conference in Ireland, Jeff described for me, you have to meet John. Okay. So in the past years, we have a lot of communication, and luckily we get one project together, work on the wave energy control for design. Today, John will talk about very special uniqueness of our wave energy. And about Professor John Ringwood, he finished his PhD in 1984 after working in Dublin City University, and he moved to Maynooth University in 2002 as a founding department chair, later become a founding dean for the founding dean of engineering. So currently he is professor in electrical engineering and director of Center for Ocean Energy Research. He won many awards, published 400 peer-reviewed papers. One award is IEEE Control System Mechanism Outstanding Paper Award. Okay. He also won French government award. Beyond that, he also held some commercialization effort and won commercialization award. Okay. So John also loves music. And in addition, his PhD study in engineering, he has a master's degree in music. Okay, thank you, John.
Thanks. Well, first of all, just thanks to Leah and the College of Engineering for the invitation to come here. I mean, University of Michigan is a very prestigious institution, and I understand that this seminar series has been running since the 1960s. So it's a great honor to have the opportunity to present to you. So the presentation is in two parts. I'm going to say a little bit about Maynooth University and the Center for Ocean Energy Research. And then there's a sort of I call it a semi-technical presentation, which tries to put the wave energy control problem somewhat within the context of more traditional control problems, or what we understand to be at least the control sciences addressing more traditional control objectives. So first of all, a little bit about Maynooth itself. So Ireland is a small country, but Maynooth is also a small town within Ireland. It's about 20 kilometers. That's about 12 or 13 miles of your miles to the west of Dublin. And it's really a university town. Maynooth University started as a seminary a little over 200 years ago to train priests, and it still has a seminary on campus, although that's a separate institution now, and this is just one of the engineering buildings here. So wave energy, if you ask somebody to describe a wind turbine to you, they'll be able to draw, a vertical pole with a three-bladed propeller on it, and we've all seen them. But wave energy devices are quite well. They have many forms and shapes. They exploit lots of different operating procedures and principles. So they all look quite different. These are just four devices: hinge barge, a two-body heaving buoy, oscillating water column, and an oscillating wave surge converter. And there are many, many more. And there are maybe more than 200 prototypes that have been developed. And there is really no technology convergence. So in addition to being a relatively new problem, it's also a problem that's spread across a lot of different technologies and a lot of different platforms. I guess principally people imagine that we would use the power of ocean waves to generate electricity, but there are also some other applications, such as the production of potable water and to power remote data buoys as well. I mean, at the moment, the sort of levelized cost of wave power is way in excess of wind and most other generating modalities. So it's not really an economic proposition at the moment. Our own center was founded in 2001, and pretty much by accident. There was a a guy who just finished his degree in University College Dublin, who lived very close to the university, and he was passing the university one day, and he thought he'd call in to see if there was any interesting PhD projects. So I did my best to excite him about the interesting projects that we were doing, and he wasn't very excited. So he said, "Can I propose my own project?" And I said, "Sure, but we're going to have to find some funding for you." So 2 weeks later, he came back in and he said, "There's a guy down the road that's looking for a controller for a wave energy converter." And I said, "What's a wave energy converter?" And that was the start of it. And I learned a bit more since then. So now we have around 35 people in the group, made up of academics, researchers, these honorary fellows that I'll mention a little bit about, and also interns and various visitors that come and go. It's very multidisciplinary. My own background is in electronic engineering. But we typically have a lot of mechanical engineers, people from control, mathematics, physics, computer science, and fluid mechanics, and various other disciplines as well. So it encompasses all of these disciplines. I guess our core activity, or where we would consider our core expertise, is on this side here. Is looking particularly at the control design, estimator design, and forecasting aspects related to wave energy converters. And of course, as any of us who are involved in control know, that you need some sort of a model somewhere, at the very least, that describes the physics of the system that you're trying to deal with, provides probably a simulation platform for it, maybe a platform for model-based control, and a way to evaluate the operation of your controller. We've quite a few industry partnerships, and they're very important to us, not least to inspire the problems that we work on, but also they provide large-scale experimental facilities effectively for us. We have some experimental facilities in the lab, but they're generally related to hardware in the loop rigs. We don't have a wave tank, but we use wave tanks elsewhere, typically in Denmark, in Scotland, in France, and in Germany. And then we have some high fidelity numerical simulation tools as well. So a variety of platforms to work on. So I'm not going to go through everybody here, but let me just say that we have these different categories of people, all of who are equally important to the operation of the center. So we have some academics and our lab manager, Carrie. We have these honorary research fellows, which is the sort of a term that I coined a few years ago. And they're basically people who are former COER members who are now in different places. So Bing Young's back in China, and Tom is still in Ireland. Christian's back in Germany, Nicholas is in Italy, Damien's in Argentina, and Yerai is in the Basque Country. But they all still remain closely connected to the center, and they still participate in joint supervision of PhDs and areas like that. And they all have their own particular expertise, which they still contribute to the center, which is very important to us. And then we have a bunch of postdocs, and we've a new one coming shortly, and a bunch of PhD students. And we've 3 additional appointments to make. And then, importantly for us, we take a bunch of interns every year from a variety of countries, all of who add to the sort of spice of the lab. So I'll just go through a few of the current projects that we have, just to give you a sort of a flavor for what we do. So this is a project which is funded by NSF, and it's a tripartite project between the US, Northern Ireland, and the south of Ireland. And it's quite a challenging project computationally. It's a control co-design project, which aims to not only optimize the control of these devices, but also the design of the system itself. And the design in this case relates to both the array layout, but also the individual geometry of each WEC in the system. So we have a whole range of nested optimization loops. So computational efficiency is absolutely paramount in that case. This is a niche application. So looking at wave power data buoys for measuring both the sea conditions, but also some environmental variables as well. It's funded by the Marine Institute. Although we only have 1 PhD working on it, we have a whole host of collaborators, and indeed we've added to that list of collaborators in the meantime as well, which I guess on the one part reflects the multidisciplinary nature of the project and its various needs. And then we have a visitor from Tsinghua University at the moment that's working on an interesting project related to control co-design, And it's about evaluating the control operation without implementing it in real time. Because one of the difficulties up here is to do the computation. So we're trying to do the computation faster without the need to implement and simulate in the time domain the control action itself. This is a major project that we started about a year ago called the Sea Change Project. Rather than pursue a technical objective of power or energy maximization, here we're trying to explicitly reduce the levelized cost of energy, because ultimately that's the thing that decides whether this will be utilized in the real world or not. We have a US partner in the University of Illinois and NREL, Danish Technological University, and 3 different wave energy companies between Sweden and the UK. And it sort of follows this philosophy here that Joachim Weber developed when he was at Maynooth University. He's now in NREL as head of the water power program. And his philosophy said that, well, if you look at the 2 sort of trajectories here in terms of development, most focus is on what we call technology readiness level, which goes from sort of 1 to 9, where 9 says that you're ready to buy one of these off the shelf and it'll work and it's been tested. While 1 means that it's sort of on a piece of paper in somebody's laboratory. And somewhere in the middle, there are these various levels of scale testing and various levels of confidence in the operation of it. But what none of these technology readiness levels measure is how well it performs. And the performance we should measure in terms of economic performance, again, something related to levelized cost of energy. And Joachim's argument was that most people race out this axis here to try to get a device into the water. And that's often driven by investor needs. So as soon as private investment becomes involved in wave energy companies, they want to get the thing to market as soon as possible. They want to have something to advertise. They want to demonstrate it at large scale. But unfortunately, at that stage, the costs also get very, very high. And you only really get 1 shot at that. And at that stage, if your technology performance level is not high enough, you don't get a second bite at the cherry. So Joachim's philosophy was to move up this scale here first before moving out here. And control plays an important part of that in trying to improve the performance at small scale and at simulation level. And also the use of high fidelity numerical models comes into play at these low TRLs. And that's where we try and move up this curve here. So that's what this project really focuses on. We finished an interesting project which was funded by the European Union just earlier this year in March. It was a 3.5-year project funded by the European Union working on the development of cyclorotor wave energy technology. And that's an interesting one because it has some connections with aerodynamics where people understand how to harness energy from the air pretty well. So it's a lift-based device, and it has a lot of control possibilities, including the rotational torque that we can apply to the generator, the pitch that we apply to the foils here. And on some of them, you can also move the radius in and out, and you can also modulate the depth at which the device sits. So a lot of different control mechanisms. Some are short-term ones, some are longer-term ones, but a very rich control problem. And we've a new project starting on that in December for 4 years as well. We're also part of MARI, which is this Marine Renewable Energy Ireland centre funded by Science Foundation Ireland. And it has now almost 200 researchers, actually, which are distributed across 11 educational institutions and around about 44 industry partners. So we have particular projects within that, but we collaborate with all the other partners in that as well. And there are quite a few international collaborators and partners involved as well. I mean, wave energy has been on the go for probably 3 or 4 decades now. It waxes and wanes in interest depending on the price of oil and the price of other renewables and concerns, obviously, about climate change. We've seen a lot of wind penetration, but the problem is that if you rely on a single wind or on a single renewable energy source, if that disappears over a short period of time, then you either have to do without, or then you switch in your fossil fuel fired plants. So having a diversity of renewables helps to give you some resilience in renewable energy. And to that end, you know, there's a value in having wave energy in addition to wind. And of course, wind has had a lot of penetration on land, and now it's gone into the ocean in terms of fixed platform wind and also floating. And as soon as you go floating, then you have opportunities to have a hybrid device, which has both wave actuation and a wind turbine. And one of the interesting possibilities here, which has been exploited in one or two studies, is that with wave actuation, so there's some wave paddles underneath this is a Danish device, that if you control this device and control those wave paddles appropriately, you can perform energy capture, but also you can help to stabilize the platform as well, which reduces the axial load on the turbine. So a double potential benefit, but there's a lot of work to be done to understand what the correct sort of configuration of this should be, particularly around the platform itself and the type of wave actuation to maximize the benefit. So this is an important project, which is with Lay here. And this is a 4-year project. And it focuses on control co-design with regard to the power takeoff, particularly, and not least in relation to the mechanical motion rectification system that Lay has pioneered as well. And that presents, again, a very interesting control problem because it's a hybrid system. It's continuous time, but it also has switching points as well. So it's a really interesting project to work on, and we look forward to continuing that with Lay. And then we have a range of smaller projects. So we have a good collaboration with 2 Swedish researchers, one of whom was working for a company Sigma in Sweden. And they have developed this Moody software, which does high fidelity mooring simulation. And that's one of the areas that we have probably been a little bit remiss in including in terms of the wave energy converter dynamics. We've uncertainty quantification. So this is a sort of a move towards robust control where you need a nominal model of the system, but also a decent quantification of the uncertainty in the system. So Quilmes University is in Argentina. It's one of our honorary research fellows as a joint co-supervisor. This joint resource assessment, again, looking at the combination of wave, wind, solar, to see if we can get a more resilient total supply, and importantly, to see how wave energy fits into that mix and what benefits it has. And a range of other projects as well. One of the interesting ones actually also is to look at how the wave resource is evolving in time. And here you have to look at very long time scales. But if you look at, there's, you know, from 1900 up to 2010, and you can see there's a sort of an average increase in, that's the total momentum, but you could either divide that into total wave power, and indeed wind power is also evolving. It depends where you are in the world. Sometimes it's going up, and some parts of the world it's actually diminishing. But we need to look at these longer term trends to understand how to best design the devices and indeed to control them as well. So the center is involved in quite a lot of dissemination activities. Again, we have a lot of collaborators, and our pretty much annual Maynooth Wave Energy Workshop is an opportunity for people to get together. We've also sort of franchised it out a little bit. So last year, we had the Maynooth Wave Energy Workshop in Italy. And this year, we'll have the Maynooth Wave Energy Workshop in Argentina. And we're going to take it back next year. So we're going to have one in Ireland. But next year also, there's going to be one in China. So it's great to see that it's, you know, it's an event or an activity that has had some success and that people want to come along to it. It's about half and half industry and academia. And it's broadly national in the country that it's organized in, but it does tend to, you know, attract a few external people from overseas as well. And then we have a number of outreach programs to try and inspire the next generation of wave energy people. So we have we built a range of small tanks with the emphasis on people being able to interact with them themselves. And usually everyone gets wet, much to the discomfort of the parents and various others around, but everyone has a bit of fun. And the most important thing is to get hands-on. And in fact, we had a project that we just finished, which was funded by the International Federation of Automatic Control, to build a very small scale wave tank of about this size here, but with a functioning wave energy device where there was active control. And what we can do is we can turn the control on and turn it off. There's a little knob to sort of tune the controller as well. So the idea is that it's a visual demonstration of the power of control within a wave energy context, and that it's interactive. So, you know, I hope to bring it to a few conferences next year. And yeah, we're always recruiting. So if anyone knows of any good people who are interested in this area, then there's some positions. Typically at the moment, they're PhD positions. And we anticipate a range of postdoc positions coming up as well. And a final note on you know, how I got to be where I am, and it's not what you might expect. I mean, at school I was not an A-grade student, and I was sort of less interested in school and more interested in playing soccer in the street with my friends. I wasn't much good at soccer either, as it happened, but it was a lot more interesting than school at the time. And I sort of, you know, just bounced through school. At the end of it, myself and my best friend, we convinced each other that we should join the Merchant Navy. And we both applied, and my friend got it and I didn't. My friend actually left 2.5 years later. I think both of us had a very unrealistic impression of what it might be. And I ended up in engineering college on the foot of an application that my mother had put in on my behalf. So that's how I ended up in engineering. And I failed all my semester 1 exams. And I really wasn't that interested. And then I just got scared that if I didn't succeed at this, what was I going to do? So I got my act together at the end of first year, got through my exams, scraped through second year, and then third year, it all just came alive for me. I just started to get interested in it, and then I found I had a little bit of aptitude for it as well. And then I got through fourth year good, and then I decided to go and do a PhD, whatever that was, right? So I had no idea what a PhD was either. But I discovered I was interested in that as well. And that, you know, I like to do new things. So when I finished the PhD, I took a job in academia because I wanted to stay in research. But the idea of teaching scared the life out of me, right? And I remember the first few classes were a little bit tense. I'm not too sure whether I was more stressed out or the students were. But we got over the first few months, and then I started to enjoy that, and then I found out a little bit of an aptitude for that as well. And you know, I guess here I am. You know, I took another job as an incoming head of department, which was a bit scary as well. But then started to enjoy that. And I think the moral of all of this is that you know, you need to take a few risks to discover who you are and what you like and what your aptitudes really are. You know, I think it's very difficult at a young age to work out, you know, what you will eventually succeed at or enjoy. And I think you have to enjoy what you do. So for those students out there, particularly, you know, be prepared to take a few risks and stick your neck out, and you'll be surprised what you'll find out about yourself. Oops, sorry. So this is the sort of semi-technical part of the presentation. And what I'm going to do is cover what I call these paradoxes in wave energy control that sort of fly in the face of what we understand maybe in the more traditional control sciences. And I define a control paradox in wave energy as a characteristic of wave energy control systems that is not what you expect in the more traditional control sciences. And the main reason for that is that the control objective is different. So typically in you know, most of the control sciences, and there's a, remember reading the, you know, an encyclopedia of control, and pretty much from cover to cover, it deals with, you know, a tracking problem or a regulation problem. So usually we're trying to minimize an error or minimize a state, and it's usually a quadratic version of that. So we get, you know, something approaching a nice convex problem. Of course, that doesn't mean to say that the system's not complicated and it doesn't have nonlinearities and stuff, but the control objective itself is instrumental in I think, in making the wave energy control problem a little bit challenging. There are some analogies with wind energy, but they only go so far. I should also say that I'm not much of a hydrodynamicist. So, you know, that also presents a challenge. It presents a challenge to me. So I have people that are good at hydrodynamics, and we need multidisciplinary people involved in this as well to be able to solve the totality of the problem. So let me, in my own simple way, try and describe, just set the scene for the sort of problems that we're going to solve. So let's assume a simple wave energy device. So we have some floating body here. There's the still water level, and that's going to move with the waves. It exerts an excitation force here on the device. And that in turn produces a force on this power takeoff. And you can imagine that that's something like a linear generator. Okay, so we've maybe the translator's moving and the stator is fixed at the bottom. And we can control the force in here. So that's our control signal there. The velocity of device is here, and we'll talk a little bit about that. So the power, the useful power that's converted in the device is simply the product of this control force times the velocity, and the energy is the time integral of that. So Cummins equation has been around for quite a while, and it's a relatively simple way to describe the hydrodynamics or the dynamics in total of that device. It has certain assumptions, which are all these ones here. And one of the very limiting assumptions, which I'll maybe revisit, is this idea of small oscillations. So it assumes that the body is not moving very much in order to satisfy the linearizing assumptions. So this is a Cummins equation. It's an integral differential equation. So we have a sort of a mass term here, or an inertial term here. We have a damping term here, and then we have a restoring force term here. And the system is driven by two forces. One is the wave excitation, where eta refers to the free surface. That's the surface of the water. And then this control force that we can apply. The hydrodynamic parameters are these things here. So this infinite frequency added mass. We have this convolution kernel here related to radiation damping. Radiation damping is as a result of the device motion itself. It imposes a hydrodynamic force on the device. And this convolution term relates the excitation force impacted on the device as a result of variations in the free surface. And we can use a variety of different techniques to determine these hydrodynamic parameters. And also, we can use a finite order approximation to turn these into finite order dynamic terms so that the whole thing results in a slightly higher order differential equation. Okay. So that's the basic model. In terms of the control objective or the control problem statement, the ultimate objective is this levelized cost of energy. So that's basically how much your energy costs in terms of dollars per kilowatt hour. And it's made up of capital costs, operational costs, and then this is the power produced. So costs are on the top, power produced is on the bottom. So basically it's in dollars per kilowatt hour. And we usually discount that over the lifetime of a project, which is usually about 20 or 25 years. However, there are a lot of difficulties with this as a control objective. First of all, it's very long-term because the operational costs are evaluated over the 20 or 25-year lifespan of the device, whereas we need to take control decisions on a second-by-second basis. So usually what we do is we say, well, let's not worry too much about the top part. That's the hard part that's to evaluate. And also we will say that, you know, maybe the control actions or that these costs are not so sensitive to our control actions that we're taking now. And rather we look at this part here, which is very sensitive to our control actions. So usually we sort of distill this down to maximization of captured energy, subject to specific hard constraints on some of the device variables, which include the displacement, the control force, which is a fairly normal constraint in control systems, and then maybe also a constraint on velocity. So there are two broad approaches to solving this problem. We can either treat it as a maximum power transfer problem, and of course we're in an electronic engineering department here, so most people are familiar with the maximum power transfer theorem, either for DC or AC systems. And for the AC system, that's very applicable in this case, and that'll allow us to calculate at least one of our token controllers. And otherwise, we can use something like results from LQG or MPC, where we specify some sort of a cost function and we try to minimize or maximize that. And in general, the cost function can contain terms, quadratic terms in the state and quadratic terms in the input. But specifically in this case, we're interested in this cross product term, which would be something like velocity times force. Okay. But the problem with this is that it essentially gives you a non-convex problem unless the weightings on R and Q are large enough. And then what you're doing is actually biasing the optimization problem a little bit. So you have to be a little bit careful with this one here. One of the things that we've done is to look at, instead of, let's say, treating it as a classic zero order whole discrete time problem, is to look at parameterizing the signals in the system using some other basis functions that better suit their nature. So for example, if we look at, typical wave-like signal, and imagine that if you're forcing a wave energy device with wave-like signals, then the other variables in the system are going to be wave-like as well. So typically, Fourier functions and these sort of pseudo-periodic functions work pretty well. The only problem with Fourier, of course, is that it has to start and finish at the same place. So you may get some discontinuities at the edges here, but there are ways around that by using either half-range Chebyshev Fourier functions or using windowing functions. And you can see that the approximation error for, some sort of an arbitrary wave-like function is very good for some of these parameterizations, while zero order hold, it only gets good as the sampling period gets very, very short. And of course, that puts a demand on your computation. And here you can see the evolution in the fit as you increase the number of basis functions. And in particular, the zero order hold goes down very slowly, while the half-range Chebyshev Fourier function, the error goes down fairly rapidly as the number of basis functions increases. So that's a sort of a smart way to represent the system and to improve the representation in a computationally efficient way. Okay, so back to the maximum power transfer theorem. So if we now calculate the ratio between velocity and force, that gives us 1 over the intrinsic system impedance. And we know from maximum power transfer that if you have a source, an AC source, which has a certain internal impedance, if we want a maximum power transfer to the load, then we make the load the complex conjugate of the internal impedance. And that's exactly what we do here. So from that, we can then determine what the optimal velocity profile to follow is, and it's related to the wave excitation force. Okay, so that is a wave energy controller. And it can be implemented here. And what's nice about it is that all you got to do is measure the device velocity. You put it back through the controller here, which remember is the complex conjugate of the system transfer function effectively. And it's really simple to implement. So it's a simple feedback structure. It looks like a sort of a traditional controller, where you have a forward path G and a feedback path H. And normally we associate that with good disturbance rejection and sensitivity properties, but we'll see that because we have this inescapable relationship between G and H in terms of the complex conjugate, that we have little design freedom really. And it can be difficult to include constraints in an optimal way as well. So alternatively, going back to this relationship here, we can use a feed-forward structure and have an optimal velocity reference, which we then follow using a traditional velocity tracking loop. And the hard part now is coming up with this guy here. And I've represented it as a function of S, but in reality, it's a problem to solve in the time domain, an optimization problem. And essentially, it's a feed-forward structure. And normally when we hear feed-forward in control, we think, oh, that's not very good, high sensitivity, right? So feedback normally gives us good sensitivity, feed-forward, bad sensitivity. A little bit different in the wave energy case. What this does require, unfortunately, is a measure of the excitation force, which is an unmeasurable quantity in the wave energy case, but you can build an estimator to estimate it. Okay, so the first paradox. Wave energy controllers based on linear models invalidate the assumptions on which those models are built. So if you take a traditional tracking control problem, so for example, the control of the temperature in the room here, you know, we might set it at 18 degrees. Maybe you guys like it a little bit warmer here. You know, we're good with 18 in Ireland. And, you know, when we switch the controller on, then, you know, we either heat or cool the room so that it reaches the set point. And after that, the controller does everything in its power to keep it at that set point. So the tendency is to push it towards that point, the set point, where we can reasonably linearize the system model around, because the controller is trying to keep it there. Okay. In wave energy, it's almost the complete opposite. So we switch the controller on here after 2 seconds, and all that happens is the motion gets more and more aggressive and gets, you know, the variance gets larger and larger with respect to the equilibrium point about which the model is calculated. So the controller is actually shooting itself in the foot in terms of violating those linearizing assumptions. And you can see it here. There is a little video that goes with this, but I'm not going to muck around with the IT system here and tempt fate. But in essence, if you just look at the variation in the wetted surface, which is indicated by the red band here, for the uncontrolled case, there is no external force being applied, only the waves. And generally what the device does, it just follows the waves. As the waves goes up, it goes up, the wave goes down, it goes down, and the variation in the wetted surface is quite small. But in the controlled case, we apply an external force, which is going to change the amount of wetted surface that appears and disappears. And if you look at the phase plane, so this is the difference between the displacement of the device and the free surface. So it's very much the variation in wetted surface. And here's the variation in the velocity of the waves relative to the velocity of the device. You can see that the operational space in the controlled case, which is the red one, is much, much greater than the uncontrolled case. So the operational space is way larger. We've developed a model maybe based on this here. And now we're in this scenario here as soon as we implement the control. So this puts us in a little bit of a difficult position. And I mean, in hydrodynamic terms, this would tend to excite nonlinear Fruit-Koloff forces, and this would excite viscous drag forces. If you look at the validity of different models in the controlled and the uncontrolled case, I'll just run through these very, very quickly. So the linear model is the L model, so you can see here. And there's a blue one as well up here. I haven't annotated all of those. Then a nonlinear model with a nonlinear static Fruit-Koloff force. So it's a nonlinear restoring force term. And then these two have nonlinear restoring force, but they're fully nonlinear in terms of the dynamic Fruit-Koloff force as well. One is an algebraic model, the other is a remeshing model. And then we take those models and we add on viscous drag term. And then finally, CFD, or computational fluid dynamics, is our sort of gold standard, normalized to 1 in terms of fidelity. Okay. And what happens in the uncontrolled case, this is the blue circles, they're all pretty good. You know, they all work pretty well, and they're all pretty close to the fidelity of the CFD model. But as soon as you switch the controller on, they nearly all fall away, apart from this last model, which is the one with the static and dynamic nonlinear Fruit-Koloff forces and the viscous drag. Okay. So a radical difference between the fidelity of the models in the controlled and the uncontrolled case. And how do we get around that? Well, we can use nonlinear control. And we do have a version of a nonlinear controller which does present a convex optimization problem, and we have managed to implement it in real time. I'm going to focus here in the interest of time just on the problems rather than on, and I'm sure we can share these slides if anyone is interested in following stuff up. But let me move on to paradox 2. So the wave energy control solution is non-causal and typically requires the value of an unmeasurable quantity, which is this excitation force. So, and it relates back to this complex conjugate, because we're taking a complex conjugate of a causal quantity, so the solution is in turn non-causal. We can measure the excitation force only if the device is held stationary and we have some load cells or something like that on it. So we could use that as training data for an estimator, data-based estimator, but you can build an estimator based on physical models as well. And then you can use a simple autoregressive model actually to do the forecast that we need. But you can also get around. So the estimation and forecasting is the sort of the long-winded way to solve it. But you can also solve it as a causal problem and come up with the best causal or suboptimal solution. And of course, Jeff has been leading the effort in that score. And particularly, the industrial partners like that because it's a simpler controller. It doesn't have estimation requirements and it doesn't have forecasting requirements. So two routes to go to deal with that one. Okay, paradox 3. And again, I'm delighted to be in an electrical engineering department because I've showed these slides to some mechanical engineering people and their eyes glaze over. What's this triangle thing here? But I'm hoping that some people recognize an op-amp anyway here. So wave energy control systems degenerate the sensitivity properties of the control system. Whereas normally when we we control a system, we expect there to be some feedback in the system and you naturally get, with some reasonably high gain in your feedback at particular frequencies, you get nice disturbance rejection and sensitivity properties. And this is exemplified in the op-amp case. And of course, this was pioneered by Black with his, amplifiers for the communication lines that allowed long communication lines to be built with some stability. And typically when you buy an op-amp like a 741, they'll tell you that the gain is somewhere between 25,000 and 400,000. And they're not going to tell you the right answer because they don't know. They're not built to that tolerance. But once you put feedback around them, everything is good. And you find that the sensitivity of the system to variations in the gain of the op-amp is tiny. So that means that even if you have 100% change in the gain value, the real gain value, then the overall change in the input-output gain is something like 0.001%. So that's nice. That's very comforting. And that's what we expect with traditional feedback control systems. So here's what looks like a traditional control system. But now we have this complex conjugate relationship between G and H. And the sensitivity function is quite scary. I mean, look at the numbers here. The base value is 0, and it's in dBs, right? So it's log scale. And there's 0 dBs. The only frequency at which the thing is decent is at the resonant frequency of the device. So this is the wave frequency. So when the wave frequency is coincident with the device resonant frequency, things are good. But at that frequency, the controller is actually not doing anything. It's doing nothing at all. And it's only when you start moving away from that, the controller starts to be active, and then your sensitivity function becomes enormous. So it looks like from an input-output point of view, the system is extremely sensitive to variations in the model of the system. And I've also plotted the variations to the sensitivity to the mass, to the damping term, and to restoring force term, and they're all equally bad. But, well, to ask the question, is the closed loop system sensitivity important? Remember, what we're trying to do here is not track the output necessarily. We're trying to maximize power production. So one of the things we could look at is whether, it's equally bad in terms of power production, in terms of sensitivity. And going back to the idea of feed forward and feedback, this is a feedback structure, so I expect from a traditional point of view that sensitivity would be good and feed forward would be bad, but in fact, the results are variable. So with regards to errors in inertia or stiffness, for the ACC controller, that's a feedback controller, it's pretty bad. Things are okay when there's no error, right? So this is the error in the imaginary term of the intrinsic impedance. And we're looking at the ratio of actual power to optimal power, right? So when actual power and optimal power are equal, in other words, you're getting nominal power, then you get a value of 1 here. And that's the case for the ABT controller. So that's the feed-forward controller is insensitive to errors in inertia or stiffness terms, right? So that's nice. But the feedback controller, on the contrary, depending on which particular frequency it's customized for, can give you very poor performance. In other words, the actual power drops off dramatically as the error in the imaginary term gets large. It's the opposite for the damping. In the damping case, the feedback controller, the ACC controller, is actually pretty good. And the AVT controller then has problems with negative errors in damping. So that says that, well, if you're going to get some modeling errors, you better overestimate than underestimate, right, for the AVT controller. And the solution to this, of course, is that, well, we can treat it as a robust control problem, but we can't use standard H infinity techniques because our performance objective is a little bit different. So there are solutions knocking around. Paradox 4, the last one. So wave energy control systems increase the complexity of estimation, forecasting, and control in arrays, right? And we're all familiar with wind farms. So normally we're not, you see the odd isolated wind turbine, but mostly they're deployed for good economic and scale reasons in farms. And it will be the same with wave energy devices. And the more devices you put in, you start to get quite a complex wave field. So you have the incident waves, but each of the devices is moving, so it's radiating waves. One of the nice things is that you can actually have constructive interference as well as destructive interference. So in a wind farm, normally you get wind shadowing. It's always destructive. In a wave farm, depending on the spacing and the motion of the devices, you can get constructive interference between the radiated waves and the incident waves. So the answer, one of the answers to this is to look at the complete system and have a complete system model. So we develop a controller using that complete model, which ends up being reasonably complex, but it works quite well. So it's able to anticipate all of the radiated waves, and it's able to control devices so that on average, they all produce constructive interference, right? So we looked at, well, just in this example here, there's 3 different layouts. And here we plot the ratio of independent control to global control. So always the global control, depending on the layout, works to a greater or lesser extent, much better than independent control. So here you can see we're down at a value of 0.8. So that means that the independent controllers are only giving you 80% of the power that you would get from global control. Okay, so that's a bit of a benefit, but it's problematic when the arrays become very large because the dimension of the model becomes very large. So one of the things we're interested in, and I was having a conversation earlier with somebody, is looking at decentralized control, which is a little more economical. And in fact, the radiated waves fall off as 1 over the distance as well. So that makes sense from a sort of a topological perspective. There's also an issue in terms of estimation, because trying to estimate the excitation force on each device, which we need for control, now becomes more problematic in the array case because of this more complex wave field. But again, a global estimator, which has a complete model of the system, because even though we have a more complicated wave field, we have got a whole range of measurements that we can use. So each of the devices themselves act as a measurement point. And even though you can't measure the excitation force directly, you can use an estimator on each of them. And you keep more or less nominal goodness of fit in terms of the estimator with this global estimator compared to a local estimator. As the distance between devices becomes very large, the effective interactions become very small, and therefore the sort of difference between the independent and the global estimator becomes almost negligible. Okay, and a few other little interesting ditties that sort of come out of it as well. Yeah, so this complex conjugate control results in actually supplying power to the system over part of the wave cycle. And we can find that under certain conditions, you get very large peak to average ratios in not just the forward power, but also these peak reactive power flows. And what we'd like to do is constrain those to the sort of, the power specification of our power takeoff system, which includes the generator and the power electronics, so that we're not over specifying the system just for some small peaks. But it turns out that that's a very nasty optimization problem with the nonlinear constraint in it. But recently we've shown that these extreme reactive power requirements are really due to system controller model mismatch. So really we should put our effort not into constraining the negative power flow, but to getting a better model of the system upon which to base the controller. And then one of the things that is an issue and was mentioned in the seminar earlier on is that of persistent excitation, especially in data-driven or adaptive systems. And it turns out that because we're in waves, we have persistent excitation. So actually, it's one of the nice things about wave energy. Okay, some conclusions. So yes, we can use some tools from the traditional control toolbox, but we have to be a little bit careful. But many can be used from areas such as system identification or data-driven control. Velocity tracking is a standard tracking control or a regulation problem, and forecasting and prediction. So the things that make wave energy or wave energy array control a challenging problem are typically the sort of natural non-convexity of the performance function, especially if the system is specified in a standard zero-order hold representation. It turns out that neither the feedback nor the feed-forward structures are entirely optimal, but in different ways. So one suffers from poor sensitivity in one way, one suffers from poor sensitivity in another way. The feedback one has some difficulties in implementing hard constraints, while the feed-forward one has got a forecasting requirement. And in both cases, there are these less than ideal sensitivity characteristics. But at least if we know what the problems are, we can put our efforts into either making sure we get a particular part of the model right if we're going to use a particular sort of control. And going back to the first page, in terms of what the ultimate goal is to reduce levelized cost of energy. So converted energy maximization may, in certain instances especially, be a poor surrogate for minimizing a levelized cost of energy. But the difficulty is in estimating things like CapEx and OpEx, and particularly operational costs are a difficult one. And certainly, although I've been involved in this problem and a number of other people here have as well, for quite a while, there is absolutely plenty of scope for others to get involved. So if anyone wants to play, the playground is open. Right, and there's a few, if anyone wants to read a little bit more, these are sort of easy to read. There's just loads of pictures in this one. Say a few less pictures than that one, good few pictures in this one. So easy reading, and thanks for your attention.
And now we move to
Professor, I have a quick question about the flat array. So in your figure, it shows the influence for the power output with the dimension in dimensionless. But how is the dimension defined? It's divided by the significant length of the device or the wavelength?
Yeah. So in that particular instance, I think it was the number of diameters.
Okay.
So it's a normalized distance. Yeah, it's the number of diameters away. I mean, once you get to about 10 diameters away for a round device, it's pretty died off.
In that work, how's the mooring and the deployment considered for the array? So it's like a separate mooring for.
Okay, so that's a very good point. I mean, here we're looking just at the hydrodynamics of the system and trying to optimize the control in relation to hydrodynamics. In relation to going back to levelized cost of energy, I mean, moorings are going to be a very costly component in the system, right? And the ability to share moorings will be a major issue, right, in the economy of moorings. We haven't looked at moorings here, right? I mean, the other thing is electrical interconnection. That's going to be a major cost component. And all of these point to the need to look at levelized cost of energy rather than just produce power based on hydrodynamic considerations. So it's a good point.
Okay. Yeah, so thank you for the very nice talk. I've got two questions, one maybe a quick one, and then one maybe
for coffee.
Yeah. Well, we're gonna dinner too later, but we'll try the questions out now. So I'm new to the playground of wave energy, but I'm looking, going to be joining here with this latest project. So I saw in the preliminaries. One of the things you mentioned was you were talking about the non-convexity of the objective function, particularly if you have a work term in that objective function, which is really the term that you kind of care about, whereas the quadratic terms in X and U are maybe kind of artificial
Frills,
terms. But then I was thinking, well, the work term is when you want to maximize, right? So would that not be associated with a negative definite? I forget if it was a P matrix or what the matrix was, and if so, because that matrix is negative definite, would that not give you the problems that
I
I guess it still would, because you would have two negative definites on the diagonal.
Yeah, I mean, I don't think in that natural formulation, people have come up with a convex representation. I mean, what some people have done, and Jeff's going to answer your question, which is great. but what some people do is either use one of these parameterizations. But for example, some of our colleagues in University College Cork have used a first order whole representation, which actually gives you a convex representation, which is nice.
I'm now actually convincing myself that I have
Good. Sometimes you just need to talk out loud to yourself.
Okay, the more insightful, interesting question is in the sites that you're looking at. I'm sure this would be site dependent, but what are sort of the timescales over which the significant wave heights and periods are changing? And what I'm kind of getting at here is if the timescales are hours or days over which the significant wave heights and periods will remain relatively consistent, is there an opportunity to use learning over that period of time in order to learn the optimal control?
Absolutely, and it's an interesting question because, you know, depending on the nature of your controller, I mean, optimizing controllers generally work on the fly, so you don't have to pre-specify what the wave spectrum is generally. For these feedback controllers, for example, they usually use a key frequency, and that's either the peak energy frequency or the peak of the C spectrum, right? That moves with time. So then you could imagine using, and people use reinforcement learning for those. In terms of how quick things change, you know, usually the sort of shortest period over which you would have a consistent C state is around about 20 minutes, right? So there's plenty of time to do that either a lookup table or use your learning or adaptation. In fact, we've used adaptive controllers to deal with that as well. I mean, what would happen even if you have a time domain based optimal controller is you're still going to have some model mismatch and nonlinearity in the system, which may be greater or lesser exercised in some C states, you know, which may give you the need for relearning and adaptation in any case. Not necessarily related to the C state itself, but the effect of the C state on the model.
Makes sense. Thank you.
Jeff,
Do we have time?
There's probably somebody waiting to come in, is there?
Well,
I think you guys are gonna wanna talk about this for the next half an hour, so.
Yeah.
Maybe let's give our speaker another round of applause and